Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. This lecture is part of the Power System Operation and Control course. And in this lecture, I will discuss the step-by-step or point-by-point solution of the swing equation. And in this lecture, we will be having a profile of accelerating power of a machine, and we will have the profile of the rotor mechanical speed of the machine, and we will have a profile of the rotor angle delta. So delta is the rotor angle with respect to the synchronously rotating reference frame as we discussed in our previous lectures. And the profile of power has been discretized, okay, in this way. And we have three time steps which are considered in this step by step or point by point solution method. This is the step n. This is time step n minus 1. This is time step n minus 2. And at this point, we have a power value which is equal to PAN. At this point, we have the power value which is PA at n minus 1, and this is PA at n minus 2. So the power at each step is a constant from the midpoint of the previous step to the midpoint of the next step, right? So this is the previous step, and this is the next step, and in between we have this point, and up to this point and from the midpoint of the previous time step, the power will be considered as constant. And again, the power value at this point is PA at n minus 1, which will be assumed as constant from this point up to this point. And power will be considered as constant and equal to PAN from this point up to this point. So this is the assumption of a power profile when we are discretizing it, and this is the actual power profile. Similarly, we have also discretized the rotor mechanical speed, and here we have the time step n. This is time step n minus 1, this is time step n minus 2. But for the rotor mechanical speed, the value of omega r has been considered between the two time steps, right? So this is n minus 1, this is time n minus 2, and in between we have this value which is omega r at n minus 3 by 2, right? Or n minus 1.5. So this point is n minus 1.5 or n minus 3 by 2. And at this point, omega r is equal to omega r at n minus 3 by 2. And it will be considered as constant from this point up to this point. And for the next sample from n minus 1 to n minus, from n minus 1 to n, the omega r has been considered as constant, and its value is equal to omega r at n minus 1 by 2. So this point is n minus 1 by 2 or n minus 0.5, and this is omega r at n plus 1 by 2. So these values are considered in between the power values. Power values are defined at the time steps, and omega r values are defined in between the two time steps. And the reason will be clear to you later. And this is delta omega r, which is the difference between the two successive values of the rotor mechanical speed. Again, this is our actual omega r profile, and these staircase are the assumed discretized profile of omega r. And this is the final profile of the rotor angle, and this is n minus 1, and this is n minus 2. So at this point, this is delta n, this is delta n minus 1, and this is delta at n minus 2. And between two successive time steps, we have delta delta n over here, which is equal to delta n minus delta n minus 1. Similarly, this is delta delta n minus 1, and it is equal to delta n minus 1 minus delta n minus 2. So now let's start solving the swing equation, and we will start the solution by assuming delta delta n equal to delta n minus delta n minus 1. And we know that delta omega over delta t is equal to d omega over dt when delta t is very, very small or delta t approaches 0. So delta omega can be written as d omega over dt into delta t, and delta omega is equal to omega r at n plus 1 by 2 minus omega r at n minus 1 by 2. And this is also delta omega, which is omega r at n minus 1 by 2 minus omega r at n minus 3 by 2. So this is also delta omega, and it is equal to d omega over dt into delta t. And d omega over dt is the rate of change of angular velocity, which is equal to d square delta over dt square. And it is equal to the angular acceleration multiplied by delta t. And d square delta over dt square is equal to pi f over h into pa according to the swing equation. And here we will have delta t. So here we are assuming omega r values between n minus 1 by 2 and n minus 3 by 2. So which value of power will be considered in this case? So omega r at n minus 1 by 2 is this, and omega r at n minus 3 by 2 is actually this value, right? So this is omega r at n minus 1 by 2, this is omega r at n minus 3 by 2. So in between these 2 points, we will have PA at n minus 1. Okay, so this is omega r at n minus 1 by 2, this is omega r at n minus 3 by 2. So in between these 2 points, the value of power will be considered, which is defined as PA at n minus 1. So that's why the power values are present in between the two successive samples of rotor mechanical speed. Similarly, rotor mechanical speed is defined in between two successive samples of the accelerating power. So actually this is the reason. So here we are considering the difference of these two values of rotor mechanical speed. So in between these two values, we will consider the value of power, which is equal to PA at n minus 1 multiplied by delta t. Now, say in the same way, we can write delta delta equal to d delta over dt multiplied by delta t. Okay, so let's assume delta delta n minus 1, which is equal to delta n minus 1 minus delta n minus 2. So that can be written as omega r at n minus 3 by 2 into delta t, right? Because delta delta is equal to d delta over dt multiplied by delta t. D delta over dt is equal to omega r. Now we are considering the difference of delta n minus 1 and delta n minus 2. So this is delta n minus 1, this is delta n minus 2. So in between these two values, we will consider the value of omega r, which is omega r at n minus 3 by 2. So that's why we have written omega r at n minus 3 by 2 over here, and this is delta t. Similarly, delta delta n is equal to delta n minus 1. And in between these two values, we will have omega r at n minus 1 by 2 multiplied by delta t. And delta delta n minus delta delta n minus 1 can be evaluated by subtracting this equation from this equation, right? Delta delta n minus delta delta n minus 1 is equal to this minus this. So omega r at n minus 1 by 2 minus omega r at n minus 3 by 2 multiplied by delta t. And delta n will be equal to delta delta n in this case will be equal to delta delta n minus 1. So this will be positive after moving it to the right hand side. So delta delta n minus 1 plus um this thing is actually equal to pi f over h into pa n minus 1 into delta t. So we have already evaluated this value in the previous step. So this is equal to pi f over h into pa n minus 1 multiplied by delta t. So we have another delta t over here, so that will be equal to delta t square. So that is the solution of the swing equation, and we can start solving the second order differential equation, which is the swing equation, by assuming the initial condition of the accelerating power and the rotor angle, and we can also assume the step size of the time. And after doing these assumptions, we can start numerically solving this difference equation instead of the differential equation. So with each computation we can evaluate the next value of delta delta n, and that delta delta n will be used to evaluate the next value of delta. So if we have previous value of delta, which is delta n minus 1, and if we have delta delta n minus 1, then we can evaluate delta n. Okay, so with this stepwise method, we can evaluate the values of delta and then we can plot them as a function of time. So that is all about our today's lecture, and I hope you have understood the solution of the swing equation using this difference equation method. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.